Hello, everyone. Welcome to Lecture 5 on Introductory Statistics. Now, in the last lecture, we talked about some graphical representation of the data, such as the histogram, the frequency polygon, cycle graph, or the stem and leaf display, and so on. So, well, in today's lecture, we are going to introduce some descriptive statistics. Now, in the section 1, we will talk about some measures of center, and then in section 2, we will talk about some measures of variation. Now, firstly, let's talk about section 1. Consider some popular measures of center. Now, in many cases, we are interested in some measure of center. For instance, the average weight of students of a certain group of people, right? The average household income in a region, the GDP per capita, right? So, and also CO2 emission per capita, and so on, right? So these are some sense of the center, the average. Okay, so we are, in many cases, we are interested in such measures. And these measures are sometimes called the central tendency. Now, the most popular ones are given below here. Right? So one is called the arithmetic mean or the mean, the median, or the mode. What are they? All right, so we're going to introduce all these. Now, first one is the mean. What is the mean? Okay. The arithmetic mean or the mean, okay, denoted by x bar, okay, is the result obtained when a collection of values are added and then divided by n, the number of values. Okay, so you take the summation and then divide by the number of values, which is, well, the average. But in statistics, we say the mean instead of the average. It is the same. All right, the formula is the same as taking the average, but in statistics, we say the mean. The formula is given below. Right, so x bar equals the summation is a sigma x over n, where this sigma x is the sum of the values. You take the summation of all the values in the data set. And then you divide that summation by the number of values, lowercase n. So that is the sample mean. All right, that's the sample mean. Okay. Now, if here is the sample mean. Now, if we were to calculate the arithmetic mean of a population, in other words, if the data set is a population data set, in this case, we will use the simple meal. Meal. This is the Greek letter meal represents the population mean. Okay, so in other words, the sample mean is x bar. It's a sample, it's a statistic. Well, for population mean, it is a meal, it is a parameter. Okay. Now, here is the round-off rule for the mean. Okay, for the mean, you want to carry one more decimal place than is present in the original set of values. Okay, so you carry one more decimal place than the values in the original data set. Okay, so let's consider an example here. Now consider this example. Suppose in a medical study, a researcher wished to estimate the average length of time needed for a particular nursing training to draw a series of blood specimens. A sample of the nurse's work over several months yielded the following times: 10, 6, 5, 14, 6, and 13 in minutes. Now we want to calculate the mean. Okay. Now, firstly, this is a sample data set or population data set. Now this should be a sample data set, right? Because we only have this five values here, and this is a sample data set here, apparently. So the notation for sample mean is x bar. Okay, so we use x bar instead. Okay, so we will have a solution here. So what do we do? So x bar. Now it equals a ratio. Now is firstly is a summation. On the numerator is the sum of the values. So what are the values here? So it's 10, 6, 5, 14, 6, and 13. So we are going to take the summation of these values. So 10 plus 6 plus 5 plus 14 plus 6 plus 13. And divided by, right? N is a number of values. How many values are here? So 1, 2, 3, 4, 5, 6. So in total, there are 6 values. So N equals 6. Okay. So if you add them up and divide by 6, now using the calculator, you can find this one is what? As 9. All right. But be careful here. You got to carry one more decimal place. Use 9.0 as your result. Why? Because this is a runoff rule for the mean. Carry one more decimal place than is present in the original set of values. Now, original set of values are what? Okay, they're 10, 6, 5, 14, 6, and 13. They are integers. There is no decimal place. So we carry one more decimal place. So therefore, we will have what? 9.0 as our answer. Okay, so be careful on that. Okay, basically it's very simple. Take the summation divided by the number of values. Then you got a mean. Okay. Consider another example. A dataset of airport data speed includes measures of data speeds of smartphones from 4 different carriers. Now find the mean of the 5 data speeds for Verizon. Okay, so these are given here. Now, what is the mean? Again, this is a sample data set, right? So we are again trying to use what? X bar. So here solution, we're going to X bar equals the summation 38.5 plus 50.6 plus 22.4 plus 14.1 plus 23.1. So that is going to be the summation of all the values in the data set. Now, divide by the number of values. How many values are there? So we know that there are 5 such values, right? So divide by 5. Now, using the calculator, what did you find? And be careful, how many decimal places do we need to carry for this one? Okay, so it's one more decimal place than the values in the data set. So in the data set, there's one decimal place. So we carry another decimal place, which is 2 decimal places. So therefore, we will have this one equals what? Using the calculator, you can find that this is 30.74. Be careful. All right, you carry one more decimal place than the data in the data set. Okay. So this is the X bar here, which is pretty easy. All right, very good. Now, here, let's consider some important properties of the mean. Okay. Now, firstly, sample means drawn from the same population tends to vary less than other measures of center. Okay. So you have different measures of center. Okay. But sample means, if you take the every sample mean, they vary less than other measures of center. Now, this is one of the reasons why sample mean are preferred in many applications. Now, second is the mean of a data set uses every data value. Now this is because what? We are taking the summation, then divided by n. So every single value in the data set are used, right? So for instance, if we are trying to find the average grade on test 1 in a statistics class, in our statistics class, then what? Your grade, the grade of every student has to be used in order to get the summation and then divided by the class size. Then we got what? The mean of the test 1, which is the average, right? The average grade for test 1. That is why, we can see that we have to use every data value in the data set, right? Okay, the last one is a disadvantage. Okay. Disadvantage of the mean is that just the one extreme value, an outlier in such cases, can change the value of the mean substantially. Okay, for instance, if our average is good, it looks good, like about 70 or 80, about 80 points, right? But one of us didn't do well and got 10 points out of 100, right? Just as this 10 points, this extreme value will what? Bring our average down, right? Bring our average down. So that is why this is a disadvantage of the mean. Just one extreme value can change the value of the mean substantially. I will bring our average down. Okay, that's not good. Okay, so let's work hard on this, right? So now let's consider the following example to show this. Okay, now consider the example 3.1 about this nurse in training, right, time. So if we add another observation, 51 minutes, into the sample, and now the sample consists of 7 observations, that is 10, 6, 5, 13, 6, 13, and 51 minutes. Now, let's calculate the new mean and compare it with the original mean. Okay, so let's calculate the new mean. Let's denote it as x bar new. Okay, the new mean equals what? All right, so now we're going to take the summation of all these values after adding this 51 here. So it's 10 plus 6 plus 5 plus 14 plus 6 plus 13 and plus 51. All right, over what? Over 7. Okay, so this average equals what? As you can see, you can find this one equals 15.0, right? 15.0. Be careful around one more decimal place than the values in the original data set. So this is our new mean. Okay, this is our new mean. So what is the original mean? Say this x mean old. Let's say old. The original mean equals what? Here we saw, right? So we found this is 9.0. This is the old original mean. So that's 9.0. 9.0. So as you can see, this is new, which is 15.0. This is old. This is 0.9. So let's compare them, right? So as we can see, the difference, the change in the mean is what? It's x new bar minus x old bar equals 15.0 minus 9.0 equals 6.0. All right, so you see that that's a difference of 6, which is actually, well, be careful. in this data set, okay, 6, even though it's not a very large number by itself, but if you consider this data set, it's actually a pretty big value, right? 6. From 6, you see that these values itself are 6, 5, 14, 6. And if you the average increase by 6, that's actually a lot, a really big number. And you can see that the the old average is the old mean is 9.0, the new mean is 15.0. It's almost doubled. So you can see how big a change this extreme value brings into the mean, right? So it has the mean actually changed substantially. It's from what 9.0 to 15.0, almost doubled. So this is how the extreme value can affect the mean, right? So that's what we have. Then, all right, let's consider the second measure of center. It's called the median. As we said, the mean are affected by extreme values substantially. Now, in many cases, this is not good. This is not good. Okay, so it doesn't tell the general population. For instance, the average household income in a certain region, the household income is, there are people who are really, really, really wealthy, right? So if you take the average, the mean, then that's not representing the general population, right? Because what? This average can be easily affected by what? These wealthy people. If you take the average with the wealthy people, even though the average looks good, but the majority of the people are not good, are not that well off, right? So you do not want to use the average to measure such things. Okay, so then what are the other measures should we use in such cases? Okay, let's introduce one here. That is the median. So what is a median? So the median of a data set is the middle value when the data are arranged in an increasing or decreasing order. Okay, so the median of a sample is usually denoted by x tilde or capital M or MED. That is the median of a sample. For the median, we want to again carry one more decimal place than the original data value. It's the same as the mean. The round-off rule is the same for the mean. All right, so now let's show how to find the median. So you see that it's the middle value, right? But how to find the middle value? In order to find the median, okay, we are using the following 2 steps. Step 1, you sort the values. You arrange them in order, okay, to get a sorted list, either in an increasing order or a decreasing order. That is to sort the values, okay? The second is, right here, you have to be careful. If we have 2 different situations. Now, if the number of the data values is odd, okay, the median is simply the one located in the exact middle of the sorted list. Now, this makes sense. I say that I have 5 values, 1, 2, 3, 4, and 5. Okay, so 5 is an odd number. So as you can see, there is only one located in the exact middle of the list. So therefore, when the number of data value is odd, then the median is simply the one in the exact middle, just one value in the exact middle. Now, if otherwise, if their number of data is even, for instance, I have 6, okay, so Let me just change this one. Say that I have 6 values instead. All right, now I have 6 here. Now, even then, what is the median? The median is going to be found by computing the mean of the 2 middle values in the sorted list. So you have what? 2 values in the middle, right? So you have 2 middle values. Then how to find the mean? You take the mean of the 2 values in the middle, which is the average of the middle 2. Okay, so that's how we found the median. Okay, so you want to sort the values in increasing or decreasing list, and then based on the number of data values, if it is odd, then the median is the one located in the exact middle. If the number of the data values is even, the median is going to be the average of the middle 2. Okay, so that is what we have. Okay, that is what we have. Now, consider this example. Again, is the nursing training study. Okay, so we have all these data sets, and we want to find the median. Okay, so how to find the median? Okay, we follow these steps, the steps that we introduced before. So let's see what we have. Okay, step 1, what do? We want to sort the values. Either way, in increasing or decreasing, as long as it is sorted. Let's put it in increasing order. So what we are going to have? We have smallest value is 5, 6, 6, 10, 13, and 14. That's it. Okay, this is already sorted, right? In this sorted, put it in a list. Now, step 2, how many values do we have? Okay, we have 1, 2, 3, 4, 5, 6. So there are 6 values. Since there are 6 values, which 6 is an even number, there will be 2 values in the middle. So as you can see here, that's 6 and 10 in the middle, right? So therefore, the median is the mean of the 2 middle values. 6 and 10. So that is what we're going to use x tilde, or you can use capital M, right, or MED, right? So they are notations for the median, which equals what? 6 plus 10 divided by 2, which is 8. Well, be careful. You round one more decimal place. 8.0. Okay, so you carry one more decimal place than the value in the original data set. So 8.0. Okay, so this is how we can find the median from a data set. You sort the data, and then depending on the number of values, if it is odd, it is 1 exactly in the middle. If it is even, then it is the average of the middle 2 values. Okay, so for this example, since we have 6 values, which is an odd even number, so that's why we have what the average here. Okay, that's our first example on the median. Consider another example. All right, consider this example. If we add another observation of 51 minutes to the sample, this is example 3.1, right, in the nursing training example, okay, which is the same as this one. All right, so let's add another example, add another observation, 51, and see what is the median, the new median, right? Now, the sample consists of 7 observations given here. Now, we want to calculate the new median. Can you calculate the new median and compare it with the original median? All right, so original median is just found here is 8.0. Now, if we add an extreme value like 51, right? So what is going to be the new median and compare them? Okay, so let's see. Solve this question. Okay, so solution. Now, of course, one is again sort the values. We are going to have again 5, 6, 6, 10, 13, 14, and 51. 3, 4, 5, 6, 7. Okay, this is what we have, right? This is what we have. And is this right? Yes, that's what we have. Okay, now 2. Okay, 2 is to determine there are what? How many values are there? So there are 7 values in the data set. There are 7 values, 1, 2, 3, 4, 5, 6, 7. So 7 is odd number. The median is the value located in the exact middle of the sorted list. Okay, of the sorted list. Be careful, it's always a sorted list, right? It's about this list, not this list, not the original one, all right? So it's the sorted list here. So for this one, we have 7 values, so the middle one is what? It's just a 10, right? So there is only one exact middle point, so that is 10. So therefore, let's use x tilde new to equals what? 10. Well, again, you round one more decimal place. So 10.0. Okay. 10.0 is the new median. Okay. All right. So we found out the new median. Now, compare with the original median. So we know that original median is 8.0. So it got larger. It got larger. Now, what is the change in the median? Okay, so let's see that the change in the median will be what? In the median is going to be x tilde, which is the median new, minus x tilde old. So which is what? 10.0 minus 8.0, right? So we have this here is the old one is 8.0, so that's 2.0. So it increased by 2.0. The median increased by 2.0. By adding this 51, this extreme value, the median increased by 2.0. So compare the change in the median and the change in the mean in example 3.3. Okay, example 3.3. Okay, here the change in the mean is what? 6.0. So, all right. So, the change in the mean is x bar new minus x bar old. This is, I believe it's 15.0 minus 9.0, which is 6.0. As you can see, the change in the median is 2, and the change in the mean is 60, and the change in the median is much smaller than the change in the mean, right? So the change in the median is much smaller than the change in the mean. Okay, so you can see that by adding an extreme value, 51 minutes, now our median changed by 2, increased by 2, but the mean changed by 6. The change in the median is much smaller than the change in the mean. Okay, so by this example, we would say the median is more resistant than the mean to the extreme values. Okay, so here is some important properties of the median. The median does not change by large amounts when we include a few extreme values. In other words, the median are resistant. Are resistant to extreme values. Okay. Well, the mean is not. As we can see, it changed by a lot, right? And secondly, the median does not directly use every data value. It does not use every data value. Okay. Now, for instance, if the largest value is changed to a much larger value, the median does not change. Now, let's consider this example to show it. Okay, so if we change the largest observation from 14 to 15, the new sample becomes everything else the same, except what? The 14, which used to be the largest value, is now changed to a much larger one, 51. Everything else, it stays the same. Okay, so we have 6, 13, calculate the new median and compare it with the original median. Okay, so now what is the new median for this one? Okay, solution. Now, step 1, sort the values. We're going to have 5, 6, 6, 10, 13, and 51. So this used to be 14, but now we change to 51. Okay, so in this case, there are again 6 values. So the median is x tilde equals what? The middle 2, right? 6 plus 10 divided by 2, which equals 8.0. Again, it's 8.0. Okay, so it didn't change. Right? The median does not change. Okay, so as we can see, this is 8.0, and in this one is also 8.0. So we just changed the 14 to 51, right? So the median does not change. Okay, that's what we mean. The median does not directly use every data value. Okay, so for if you change the largest value to an even larger one, the median stays the same. Okay. Next, we're going to talk about the mode. What is a mode? Okay, the mode of a data set is the most occurring value or values in the data set. Okay, this is by definition. Okay, now for the mode, leave the value as it is, without rounding. You just leave it as it is. Do not round it. Okay. The important properties is the mode can be found with qualitative data. Okay. Qualitative data, for instance, the color, right? The occupation rank, and so on, right? And so on. So that's for qualitative data. So it can be at the interval level. It can be what at a nominal level or or ordinal level. Okay. Now, for instance, let's just take an example here for colors, right? So colors, right? You have different colors of cars, the vehicles in the parking lot, right? So what is the most common colors of the cars, right, in the parking lot. So the mode can be found with the qualitative data. However, the average or the mean or the mode or the median, they cannot, right? They cannot be found with the qualitative data. Okay, so that is one. Now, a data set can have no mode, one mode, or multiple modes. Okay, so it is okay for data set to have no mode, one mode, or multiple modes. But let's just dig into this this topic. Okay, for the mode, a data set can have one mode, more than one mode, or no mode. Okay, now when two data values occur with the same greatest frequency, each one is a mode, and the data set is said to be bimodal. Okay, bimodal. If you have two data values with the same greatest frequency, then each of them is a mode, and the data set is said to be a bimodal. It's a bimodal. Okay. Now this is the first case. Now second, when more than two, right, data values occur with the same greatest frequency, then each is a mode, and the data set is said to be a multimodal. Okay, so this is multimodal. Now, when no data value is repeated, okay, so all the data values are distinct, no repetition. So we say that there is no mode. Right? This is no mode. Okay. And lastly, for the cases where all the values have the same frequency, which is greater than 1, okay, repeated, but frequency are exactly the same. Okay. In this case, there is no consensus about the existence of mode. Some argue that there is no mode, while others say all the values are modes. In this book, we would just say it is a matter of interpretation and communication. We do not take sides. Okay, so these are the different situations. You may have one mode, more than one mode, or no mode, or something like undecided, all right, something undetermined, or it is up to a matter of interpretation and communication. Now, let's consider this example. Say that the following is the number of problems, R, it should be R, or the numbers of problems that Dr. Zheng assigned for 10 different quizzes. Okay, so what is the mode? Do we have a mode for this data set? What is it? Yes, right? So we say that this is what? I believe this is 9, right? It's 9. Okay, 9 is there's only one mode, this one, right? So 9 occurs with the highest frequency, with the most occurring value, just one single one, right? So 9 is the mode. The mode is 9. And only one mode, right? So there is only one mode. Okay, so because it occurs in the most often. So it occurs most often in the data set. Okay, so this is the first one. It is the mode is 9. It occurs most often in the data set. Okay, two, the letter grades of 7 students in a statistics class is given below. Okay, let's consider this one. So what is the mode? Do we have a mode? Yes. Okay, so I believe B is the mode, right? So B occurs 3 times, A occurs twice, C and D, they just single times, right? So the letter B, mode is B. Okay, so be careful here. B, these letter grades are not numerical values, right? They're qualitative values. They're not quantitative values. Okay, so but the mode can also applies to what? This qualitative value. The mode is B. Okay. Consider this example. In a crash test, 11 cars were tested to determine what impact brake speed was required to obtain minimal bumper damage. Find the mode of the speeds given in miles per hour below. Okay, so what is the mode? What is the mode? The mode is what? Be careful. What do we have? Okay, so I believe 24. 24 have 3, right? Do we have another one? Oh, 18. 18. Okay, 18 is also a mode. Do we have others? I believe no. Right? Um, so I believe that, well, 26 they only have occurred twice, right? So I believe 24 and 18 are both modes. Now in this case, because these are two numbers, 24 and 18, they share the same greatest frequency. Okay, since they share the same, okay, greatest frequency. Since they share the greatest frequency, there's no others, right? So they just these two, they occur exactly the same number of times, and also it's the greatest frequency. So 24 and 18 are both modes. And in such cases, what do we say about the data set? Okay, the data set is what? Okay, very good. It is bimodal, right? Bimodal. Okay, so if you have two mode, we say it is bimodal. Very good. Consider another one. So a marathon race was completed by 5 participants. What is the mode of these times given in hours? So what is the mode for this one? Do we have a mode, firstly? Okay, so we do not have a mode, right? So why? Why we do not have a mode? Okay, because what? All these values are distinct. No repetition. There's no repetition of any value, right? So there is no mode. Since all the values in the dataset are distinct from each other, right? So there's no repetition here. So therefore, by definition, we know that there's no mode. Okay, there's no mode in this case. Now, consider this example. The number of cars owned by 9 households in Johnson County is given below. Let's say that, all right? Some Johnson County, I do not know, okay? So what are the modes of this data set? Do we have a mode? How do you think? 1, 1, 1, 2, 2, 2, and 3, 3, 3, 3. It seems like they have exactly the same frequency. All the values, 1, 2, 3, right? These are all the values, and they have exactly the same frequency. Okay, so the data values share the same frequency. which is 3, right? It's greater than 1. 3 is greater than 1. Okay. Now, what do we say about such cases if all the values share the same frequency? If they are repeated the same number of times. So 3 1s, 3 2s, and 3 3s. So in these cases, we would say what? The modes, some argue say that the mode does not exist. There's no mode. While others say all of them are modes, 1, 2, 3, or all modes. Okay, so in such cases, there is no consensus. It is it's up to a matter of what interpretation and um, is in communication. All right, so some say there is no mode. Others say all of them are modes. Okay. Now, we will just say what it is up to a discussion. All right. It's up to a matter. It is a matter of interpretation and communication. Okay. So let's just say that. Okay. This is the mode. Okay. Now here, let's summarize a little bit about the round-off rules for measures of center. So for the mean and the median, okay, you want to carry one more decimal place than is present in the original data set. Okay, that is the runoff rule for the mean and median. Now, however, for the mode, you leave the value as is without rounding. Okay, you just leave it as it is without rounding. You do not round the mode. Okay, so these are the runoff rules for the 3 measures of center. Okay, now we have learned some measures of center. Now let's move on to the next section. It's going to be measures of variation. Okay, so as we know, the measures of center is very commonly used, right? So what is the central tendency? What is the average? What is the mean? The the median, right? So and the mode. Okay. Now, what do we mean by the measure of variation? Why it is important to learn this? Okay. So actually, variation is one of the most important topics in statistics. Okay. So why it is so important? It is because it is used in many, many applications. Now, just to give you a simple example, so you may drink a beverage like Coca-Cola, right? So, and if you go to the supermarket, in supermarket, you will say that you want to buy Coca-Cola, the beverages, right, bottled in different bottles. So these bottles should be what? Should be more or less, the volume of these bottles should be more or less uniform. Does that make sense? Okay, so they should be what? No big variation among them. They should be more or less the same to the standard size, right? So as you can see that the bottling company, we want the bottling company to produce these bottles of volumes of uniform size, right? So if there's as less variation as possible. So as you can see, it is important, right, to be measure how uniform these bottles are from each other, right? So this is a measure of variation. So of course, it is a very important measure. Now, in social science as well, right? So you have the wealthy people, you have the wealthy and the poor, and you want what? How the income differences varies among a society. If this variation is too big, it's not good to the society, right? It's not good to the society. So you want to have a measure of variation. Now, for some of us who may do an investment, buy stock prices, the stock price tends to what? Increase or decrease. It's fluctuating all the time, right? It's either going up or down, up or down. But in certain times, during a certain time period, it may change what? Significantly, ups and downs and ups and downs, and it's just a lot of variation. But in some other period of time, it's more or less stable. It's more or less stable, right? So here again, you want to have a measure of variation. Now, in such cases, the variation represents what? Both opportunity and also what? Risks. So you have to be very careful about this. So variation is one of the most important topics in statistics. In this section, we are going to talk three important measures of variation. So the range, standard deviation, and variance. So it's going to be runoff rule, right? What are the runoff rule for this? For the range, leave the value without rounding. For the following two, the standard deviation variance, one more decimal place. We're going to talk about this as well later as well. All right, let's firstly talk about the range. So what is the range? The range of a set of data values is the difference between the maximum and the minimum. So just use the maximum minus the minimum. That is the range. So because of this definition, it has the following properties. It uses only the maximum and the minimum value, so it is very sensitive to extreme values. Right. So the range is sensitive to the extreme values. And because only maximum and the minimum value, it does not really take every value into account, and therefore does not fully, truly reflect variation among all the data values. Consider this example. Now find the range of these Verizon data speeds. Okay, so what is the range for this one? So this range equals what? Equals the largest one is 55.6 minus the smallest one, so 14.1. So that's 5, 1, 41. So 41.5. Okay, 41.5. That's the range, the maximum minus the minimum. Got range. And 10 annual salaries of these personalities from the region of this data. So the range here is 40 minus 12, which is 28, right? Very easy to find, okay? So pretty simple. Now find this one. Waiting times in minutes of customers at a bank where all customers enter a single waiting line, and a bank where customers wait in individual lines at 3 different teller windows are listed below. Okay, bank A, given this data, bank B, okay, find the range of these waiting times in both banks. Say the range for A equals what? 77 minus 6.4, which equals 1.3, right? So that's the range. We leave it as it is, right? We do not round it. So range for B equals what? 9.6 minus 4.1, which equals 5.5. Okay, so we leave it as is. We do not round it. That is the range for B. Next, let's talk about the standard deviation. So what is the standard deviation? Now here, standard deviation can be for sample data set or population data set. Okay, so for the standard deviation of a set of sample values is denoted by S, okay, is a measure of how much data values deviates away from the mean. Okay, so the formula is given here, okay, which is given this one. Now, on the top is the summation of the squares of the deviation from the mean. Right? X minus X bar is the deviation, and then you take the square, and then what? Sum up all these squared deviations, okay, and divide by n minus 1, where n is the sample size, and finally you take the square root. Now that's the sample standard deviation, okay. Now for standard deviation of a population, that's denoted by sigma. Right? This can be found using the following formula. This equals what? Square root. You want to find it for the population mean is mu. So you find the deviation from the population mean, and then you take the square and the summation all these square deviations from the population mean, and divided by what? The capital N, which is the population size, and then take the square root. So basically, these are the formulas for the standard deviation in the sample version and the population version. Okay, so they have different formulations, different formula. Be careful on this. Now, let's see how can we calculate the standard deviation of a sample or of a population. Now, consider this procedure here. Okay, so the general procedure is below. Okay, one is determine if the sample data set is a population data set or sample data set. Okay, so you want to know if it is a population data set or sample data set. Two, compute the mean. So using X bar for sample data set, mu for population data set. We want to find out what is the mean, right? And then subtract the mean from each individual value, and you got the deviation. Okay, so or what? X minus mu, right? Or X minus mu for population version. Then you square each deviations obtained from the previous step. That is what? If there is a sample, there's X minus X bar squared. This is a squared deviation from the sample mean, or you take this X minus mu square, a square of this deviation from the population mean. This step 4, and then step 5 is add all the squares. You take the squares, add them up, and then using the formula, plug in the formula right after you find these summations. All right, so you can just, this one goes to this one goes to here, right? So N is the sample values in the data set, OL is a sample data set, right? So this is a sample data set, and the capital N is defined here, right? So it's in the population size. Okay. Now, basically, what this is the general formula, the general procedure to find the standard deviation for both the population standard deviation and the sample standard deviation. Okay. So I think we are going to stop here, and we will continue in the next lecture. Thank you for your attention. I will see you in the next one.